Greetings to you all and welcome to today's webinar for the NASA Recycling in Space Challenge brought to you by 9 Sigma. My name is Brandy Heflin from 9 Sigma and I will be your host and moderator today. Please note that this webinar is being recorded. The recording and transcription will be made available on the NASA Recycling in Space Challenge page. Let's review our agenda for today. After I introduce our speakers, they will discuss the project in greater depth. Then we'll take some time addressing your questions during a live Q&A session, followed by a brief summary of project information, including how to request additional information or assistance. As we proceed through today's presentation, please feel free to ask questions at any time. We'll keep track of your questions and respond to them during the Q&A portion of the webinar. Should you need any information or assistance outside of today's webinar, please contact the 9 Sigma Provider Help Desk at phd@9sigma.com. At this time, I'd like to introduce our panelists for today's webinar. First, from NASA, we're joined by Mike Ewert, Paul Hinsey, Carissa Collini, and Annie Meyer. And from 9 Sigma, we are joined by Jonathan Yakasha. Everyone, thank you all for joining us today. We'll begin with Mike from NASA to share the challenge overview with our attendees. Mike?
Morning. Yes, to further explore the moon and Mars, NASA needs to develop new technologies to live in space longer. Think about just getting to Mars is going to take at least a half a year, sometimes closer to a year, depending on the opportunity. And so in the Advanced Exploration Systems Logistics Reduction Project, NASA is working on developing technologies to reduce the amount of items we need to take along and to be able to live longer and better in space. One of those projects is called Trash to Gas, where we take waste products that are generated and turn them back into useful commodities. So that can help us get rid of trash and recover volume within the spacecraft, and then also recover valuable resources like water, oxygen, and methane. So NASA has done some lab experiments that have focused on the type of reactor to use and microgravity issues. But now we're turning to the crowd for ideas for the best ways to feed the trash and human waste into the reactor.
Thank you, Mike. So next we'll ask Carissa to tell us about the NASA Tournament Lab. Carissa?
Hi, good morning. My name's Carissa Collini, and I am with the NASA Tournament Lab. Our team works across all of NASA with various projects and programs, as well as across different agencies in the federal government to utilize and run challenges to perform work using contracts that we have in place with crowds like 9 Sigma, like today's webinar. And what we do is we run challenges with these various crowds, and not only are we able to serve NASA with this unique set of tools, we can also help others in the federal government. This is all part of NASA's Solve. So if you ever Google NASA Solve, you can see some of the other opportunities that we have to get the public engaged. But we really see the public as a partner in making progress in not only NASA's mission, but other agencies as well.
Great, thank you, Carissa. And now we'll invite Paul to give us the background on the Trash to Gas project. Paul?
Thank you. So the Trash to Gas project took place between 2011 and 2014. Basically, we wanted to develop promising waste processing technologies that could be used during long-duration space missions. We looked at 5 different waste processing technologies, and the goals were to see which one of these could best reduce the mass of the waste, as well as generate some kind of useful product such as methane or water. The 5 technologies we looked at were called catalytic wet air oxidation, incineration or gasification, ozone oxidation, pyrolysis, and steam reforming. At the end of 2014, we did do a ranking of the 5 technologies to see which one would be the best based on our mission scenarios. However, there are other reactor options are possible depending on what exactly you want to get out of the mission. So one of these technologies may be the best if you want to produce methane, and something else may be the best if you wanted to just simply get rid of the mass of waste on your spacecraft. Some of the current and future work that we are looking at is addressing potential microgravity issues for these processes.
All right, thank you, Paul. And next up, we'll have Annie explain to us the goals of the challenge. Annie?
Thank you. Good morning. So the main things we hope to have the crowdsource effort identify are a waste receptacle and feeder mechanism that will be suitable for a microgravity environment that can deliver mission waste to the reactor for decomposition. So this receptacle and mechanism must prevent waste from floating out, leaking any fluids, and also contain the smells. Ideally, the reactor will run continuously to minimize the size and energy loss during startup and shutdown. Since we are in a spacecraft, we have limited power supply. And that means feeding waste into a hot reactor at about 300 degrees Celsius. Smaller particles entering the reactor improve efficiency. This is something that we noticed during the trash to gas project. So grinding or shredding of the waste by the feed mechanism is desirable. This can be chopping up the waste or making it, into 1-inch pieces, for example. We have not worked with micro or powder size materials, but grinding or shredding in general will be beneficial for the system. Next slide, please. So this is a picture of the general trash to gas system. You can see in the oval circle, that is the system of interest for the crowdsourcing effort. So we have the astronauts inputting their waste into the trash receptacle, which is then fed into the feed mechanism. And then we have the hot reactor zone, which is at that high temperature of 300 degrees. The product gases are formed, which then go through a heat exchanger that cools down the gas stream, where we can then have water recovery and gas recovery. Any waste that is not produced as a hot gas or fluid can be collected later on for solid recovery. So on the top left in this image is a picture of wet trash and dry trash, and I'm going to hand it over to Mike to describe what the definition of wet and dry trash is for the logistical waste.
Yeah, so on space station right now, the astronauts collect their common trash into 2 different categories, as Annie mentioned. The green bag you see there is an example of the wet trash, which might contain waste food packaging after their meals. Also in the toilet area, they collect the wipes and also wipes from cleaning up around the space station. And then in the other clear trash bag there, you can see examples of some of the dry trash components, such as clothing, other containers like toothpaste tube, or just the things you might throw in the trash at home that do not contain a lot of moisture. Not pictured are the other waste categories of the solid waste from the toilet, and we actually take the urine and distill it to recover water, but then there is a urine brine waste product that is left over as well. So those are two other categories of waste products not pictured here that would be good if we can feed those into the trash to gas system as well. And then there are some items though that would not go into this system, such as any metallic hardware, once broken hardware, those kinds of things that would be impractical to put into the reactor.
All right, thank you, Annie and Mike. And turning now to Jonathan with 9 Sigma. Could you share with our attendees some additional details about this challenge?
Of course, Brandy. First off, to our attendees, thank you all for joining today's webinar. Appreciate you being here. On this slide, you'll see the success criteria for the technology sought in this challenge. The first group on the screen shows the requirements for either the receptacle or the transfer mechanism. Whether you're proposing a receptacle or a transfer mechanism, your technology should be able to fit within a mid-deck locker. And you can see the dimensions on the screen there. I'd like to add that if your technology doesn't currently fit within that defined volume, but you believe that you do have a pathway to achieve that size, NASA is still interested. In other words, the size is not a deal breaker. Two other important specifications to note, and Annie touched on these briefly a few moments ago. The technology must not use more than 500 watts at peak power, and all user surfaces must be cool to the touch. A common question asked by respondents is technological readiness. Rather than specify a TRL, NASA is looking for technologies that could be operational within 2 to 3 years. So if you have a technology that's nearly ready for deployment, that's great. If you have a technology that's only just been prototyped, but you think it can be finalized within that time frame, that's great as well. The goal here is to identify technologies that can be ready on schedule. You can also see two criteria that are focused on the individual components themselves. The receptacle must be able to accept, at minimum, 5 kilograms of 100 kilogram per cubic meter waste. And the transfer mechanism has to be able to connect to that 300C reactor via a 2-inch opening. Next slide, please, Brandy. Here, you'll see some additional success criteria that NASA is also interested in. They're interested in technologies that can deliver other sorts of performance, and Annie touched on this briefly as well. Technologies that can, in some fashion, pre-process the waste are of interest. Anything that can increase the surface area of the waste, cut it into small pieces, extrude it, technologies such as that, or technologies that could handle both the wet and dry waste to be processed in the same batch. Another interesting component here, sensors to identify the waste. That's all of interest. So when you're preparing your responses, be sure to highlight any additional functionality that your particular technology or approach can deliver. Next slide, please. On this slide, you can see information about the awards that will be offered as a result of this challenge. NASA will issue 3 prizes for this challenge. 1 prize totaling $10,000 US and 2 $2,500 US prizes. If you're selected as a winner, you will also be recognized in announcements and profile stories. And additionally, you may have the opportunity to collaborate with NASA in the future. Keep in mind, an acceptance of a prize does grant NASA an unlimited license to use that technology. Next slide, please, Brandon. Okay, on your screen right now, you can see the challenge timeline. Moving from left to right, you can see that we launched this challenge almost a month ago in early October. Today is the webinar, November 5th. The next date on the timeline is probably one of the most important ones that our attendees are going to want to pay attention to, the deadline for submissions. All submissions have to be made online via the project page and submitted prior to 5 p.m. Eastern Standard Time on January 16th, 2019. That's a Wednesday if anybody's looking at their calendars. So if you're planning on submitting a response, I strongly encourage you to take a few moments later today or tomorrow to either create an account or log into your existing 9Sites account. That way, you can begin to review the response form and to prepare your proposal. If you need any assistance, please reach out to the 9 Sigma Provider Help Desk, as Brandy mentioned, as soon as possible. They're there to help you. Brandy will have that contact information again later on in this presentation. Brandy? Okay, obviously very important to understand the submission process. When it comes time to work on your proposal, you can access the online form by clicking on the Respond button on the project page, and you can see that on the screen right now. Please note, you'll need to be logged into your 9Sites account in order to access the response form. In the online form, you'll be asked to respond to a short series of questions about your technology. Keep in mind, all information presented must be non-confidential in nature. The goal of your response is to present interesting and compelling information about your technology, as well as your background and expertise. If you have supplementary documentation in the form of PowerPoint presentations, PDFs, white papers, what have you, you can include them with your submission. The online form will allow you to append them to your response. Please keep in mind, purely optional. If you don't have any attachment, that's not a problem. Likewise, if you have videos of your technology in action, that would be great. We'd love to see them. We ask, however, that instead of sending the video file itself, please send links to the video, such as from YouTube. In the online form, there is a section to include video links. Again, this is optional. If you do present links to videos and those videos require a password, please include those passwords in that text box as well. Please don't feel that you must complete your response all at once. The system will automatically save your information as you progress through the online response form. You can access your saved drafts via the Control Center on 9Sites. When you log in, you will see Control Center near the top. It's through there that you can access your drafts. That way, you don't have to start fresh each and every single time that you log in. And you can begin to build your response and have everything in place that you want to submit well in advance of that submission deadline. And speaking of the submission deadline, let me just say one more time that you should please make sure that you complete your response prior to the submission deadline. We're not able to accept any late submissions for this challenge. Thank you, Brandy.
Thank you, Jonathan, for that information. It's now time for the frequently asked questions. These are questions that have already been asked via the 9 Sigma Provider Help Desk or questions about 9 Sigma projects in general. Our first question that came in is, can we form teams to respond to this challenge?
Absolutely. We are welcoming responses from individuals and organizations and teams. They're all equally welcome. I will say that if you have a team that is interested in responding to this challenge, you should designate a single individual as the primary point of contact. That individual will need to have an account on 9Sites, and it is that person that will be responsible for submitting the online response.
Great. And if I can't provide both the receptacle and the transfer mechanism, can I still respond?
Again, here the answer is absolutely. Obviously, NASA would be interested in a proposal that encompasses both the receptacle and the transfer mechanism, but they are interested in approaches that simply address either the receptacle or the transfer mechanism individually.
Excellent. Now we'll open up the session to questions from the audience. Please continue to submit your questions through your Q&A chat box. This is an excellent opportunity for you to pose your questions directly to our speakers. We'll take the rest of our time today to answer them live. If we don't get to your question, don't worry. Our Q&A session is being archived and will be made available on the contest page. So, for our first question, it's about the 500-watt power absorption. Is it possible to use the 500 watts continuously 24/7, storing it into batteries for later use?
This is Mike. I'll take that one. The space station, for example, and I'm not saying that this would necessarily be used on the space station, but thinking of that as a predecessor of future spacecraft, already has a battery system to store electrical energy. So I think adding extra batteries for this particular device is not a good idea. It can take that power up to 500 watts as often as necessary, but obviously the less power it consumes, if it can go into a standby mode or something in between processes, that would be advantageous, because then that power can be redirected to other functions on the spacecraft.
Okay, thank you. And our next question is also for the NASA team. Are there any additional details about the 2-inch diameter reactor intake tube mentioned in the challenge statement?
So I'll take that one. This is Annie. At this time, we don't have the finalized system designed to share any hard requirements on that feed mechanism. All we can say is that it will be 2-inch diameter pipe, and that's basically the most information we can provide. So if Mike or Paul want to add anything, they can. Otherwise, we don't have enough public information to share the final requirements of the system.
And you can take that as a 2-inch inner diameter opening into the reactor, a metallic reactor.
Okay, thank you. And another question for the NASA team. Is the heat a continuous 300 degrees Celsius, or does it fluctuate?
This is Mike. Oh, go ahead, Paul.
Okay, yeah, this is Paul. I was going to take that one. The 300 degrees Celsius is an interface temperature with the reactor. So we don't expect that the feed system would have to interface with anything above 300 degrees Celsius.
Okay, thank you. And another question for the NASA team. What is the total distance from the trash receptacle opening to the waste reactor?
This is Mike. I'll take a shot at that one. As Annie had mentioned, the system is not completely designed yet, but I think we would leave that mainly open to the designs submitted. We're hoping that we can locate the reactor fairly close to the receptacle, and with whatever size feed mechanism you have in between. Practically speaking, I can imagine that there might be at least a few inch pipe between those, but we'll leave that up to your design, that if possible, you could locate it immediately next to the reactor.
Okay, thank you. And it seems like many of our questions coming in are for the NASA team, so we'll just stick with you until we get one that's more for 9 Sigma. What sort of potentially harmful gases can escape into the astronaut areas?
This is Annie. So we don't want any hazardous gases to escape into the crew area. So if there are hazardous gases, there would have to be a way to vent them off board the spacecraft. The safe gases that can stay within the spacecraft, at least according to how ISS operates, would be nitrogen, carbon dioxide, and oxygen, within the thresholds of the environmental control, the closed loop life support system. So we don't want any hazardous gases to leak out into the cabin.
Okay, and just to follow up on that, do you have a sense, Annie, of what kinds of gases may be produced by the waste that we're trying to confine or eliminate? I think that was the intention of the question as well.
Hey, this is Paul. So from just the waste receptacle, what you would expect to come out would be volatile organic carbon compounds, things that you would expect basically from your home trash can as it started to, if you didn't take it out, those kind of smells and things you would expect to come out of that. So a lot of the smaller volatile organic carbon compounds.
Okay, thank you.
This is Mike. I would add that, yeah, a lot of the times the most challenging or odd chemicals that we find are actually byproducts of the food.
Yes, that makes sense. Our next question, what would be the maximum weight of the receptacle?
This is Mike. Jonathan can correct me if I'm wrong, but I believe we did not place a maximum, but since this is a competition and the lower the weight, the better, that is an important criterion. We would like to see that, an estimate of the weight of the device in your design. So basically, the lower the better.
Correct, Mike. Yeah, Jonathan, we did not specify a maximum weight.
Okay, thank you. Our next question, what sort of materials can be used for insulation?
This is Annie. I would say if your system needs insulation near the hot zone of the reactor, there are resources online where you can look up insulation that has been used on spacecraft, but we want to try to go with materials that do not off-gas, that are not flammable, and that are as lightweight as possible. So, like in the past, we've used foams or ceramic-based materials. So I would go on the side of those type of materials.
Right, thank you. And another question, this one's coming to 9 Sigma. What's the largest bag size the receptacle has to accept?
Hi, this is Jonathan again. So the receptacle has to be able to accept a 5 kilogram bag of 100 kilogram per cubic meter waste. I don't know if there's a specific bag size that corresponds to that. Nessa team, maybe you'd be able to address that, but that is at least the minimum weight and density of material that would need to be accepted by the receptacle.
Jonathan, this is Mike. Yeah, that is a good question. Well, we didn't specify the exact interface that the astronaut would put the waste into. In those pictures that you saw of the wet and dry trash bags, those are about 8 or 9 inch diameter cylindrical bags. So having an opening at least that big would be very helpful. So I think that's probably the best guide we have right now. A little bit larger opening for other waste products to get them in easily would be nice. But there's no strict requirement on that.
Okay, and our next question will stay with the NASA team. Are any of the proposal reactors operating at greater than 1 atmosphere pressure? In other words, is material backflow a concern?
This is Annie. Yes, they do operate. Some do operate at higher pressures, so that would be a concern. That's a good question.
Okay, thank you. And similar to some questions that we've had, but still an important difference here. Are we talking about 18 inches by 21 inches by 21 inches for each of the 2 subsystems, receptacle and feeder, or for both together?
This is Jonathan from 9 Sigma. NASA team, correct me if I'm wrong, but I think ideally you would like the receptacle and transfer mechanism to fit within that mid-deck locker volume. Is that correct?
It's correct, but I believe we were allowing each one to be that dimension if necessary. But yes, ideally, if you can fit both within that dimension, that would be best.
Great, thanks Mike for that clarification.
All right, and our next question, staying with the NASA team. What cools the heat exchanger after the reactor? Can we use that to preheat feed?
That could be an option. However, I would say in the designs that are provided, I would not rely on that at this time. But in the future, if it's a concept that we are willing to accept and adapt, we can figure out thermal management and sharing in the future.
Okay, thank you, Annie. And another question, is mid-deck locker CAD available?
This is Mike. I do not believe we have a CAD drawing available of that.
Okay, thank you.
But we're not necessarily expecting this to fit an exact interface. That is a term and a volume used on space station, which can be helpful for doing a flight experiment. However, our focus is really more on future spacecraft. So there is some room for dimensions to be slightly different, that sort of thing. So being exactly those dimensions, I don't think is the most important thing here.
Okay, thank you. And another question for the NASA team. The equipment dimensions mentioned in the criteria, sorry, let me start that again. Do the dimensions for the equipment mentioned in the criteria include the insulation material, or will there be more room to add insulation material?
I'll start off with this one, and NASA team, please feel free to correct me here if I misspeak. The dimensions are the ideal dimensions for the proposed technologies. If your technology needs a little bit of extra space because of insulation, but you can work to reduce the size to fit within the mid-deck locker, that's still of interest. Does that sound about right, Mike, Annie, Paul?
Okay, so we still have plenty of questions coming in. We'd like to encourage our attendees to continue asking your questions. And we'd also like to remind you that if we don't get to your question during the live Q&A, we will still have the NASA team or the 9 Sigma team answer them and include those answers in the transcript that will be made available after the webinar. So is there a limit to the volume of air which can be sucked from the spacecraft and used within the 2 recycling subsystems?
This is Mike. I guess we didn't specify a limit, but you should provide that amount as that your system would require, and it would be counted against the mass of the system, because we will have to resupply that air of any that is needed to run the system.
Thank you. And our next question, still with the NASA team. How do we manage the byproducts after recycling? That is, after recycling, once we have the reusable object, what if the final product can't be recycled further? Can we dispose of it?
This is Mike. If I understood the question correctly, it's talking about downstream of the reactor, which would not be part of this challenge. But yes, there are ways to dispose of the final product, such as ash or something like that. The disposal might actually be just packing it up and storing it in place. But yes, there could be some alternate disposal. But as I said at the beginning, the focus of this challenge will be to get all of the acceptable waste products into the reactor, and that's where your challenge ends.
Yeah, and Mike, just to echo what you said, for our attendees, I believe it was on Annie's slide, she had a schematic diagram of the flow from astronaut input to the end waste products. That oval that you see on screen, that's the area of interest for this particular challenge. How to a usable receptacle for the astronaut to put the waste into, and then the transfer mechanism to take it from that receptacle and deliver it to the reactor. That's your focus for this challenge.
Thank you for that. We have a follow-up question, or along those same lines. Are you looking to build new parts in space using the recycled material rather than bringing it back to Earth?
So this is Paul. The past trash to gas work focused mostly on converting the waste materials into a commodity that could be used in space, like methane to be used as a propellant, or water/oxygen, which would go back into the life support system. There is a possibility to reuse some of the solids materials and convert them into other, a part or something that you could use in space as well. But the past work is mostly focused on generating those commodities that, like I said, could go back into life support system or a propellant.
Thank you. And again, we've got plenty of questions still rolling in here. Is pre-processing of all materials, including high-density plastics, at equal effectiveness necessary?
Can you repeat that question, please?
Sure. I'll reword it just a little bit. Is it necessary to pre-process all of the materials, including high-density plastics, to the same effectiveness needed?
I think the question's kind of going towards, do we have to pre-process everything exactly the same regardless of what the material is? I think that's what the question is after, Paul.
So I think if I understand correctly, does the trash going into the feed mechanism and going into the reactor all have to be processed to the same size roughly? I would say the answer is no. It's obviously going to be mixed trash with different sizes. So it's not like the high density polyethylene all has to be cut into perfect squares or something like that, if I'm understanding correctly.
Annie, I think your understanding of the question is pretty much in line with mine. So I think your answer probably covers it. For the individual who submitted that question, if we didn't sufficiently address your question, please feel free to resubmit a clarification and we'll try to get to it.
Thank you. And again, for the NASA team, are there any requirements related to serviceability, like maintenance, MTTF, MTBF, spare parts, etc.?
This is Mike. That's a very good and insightful question. I would say, though, at this stage of development, no, there would not be specific requirements, but anything the responders can add as far as advantages of low or no maintenance needed, long life, or serviceability if needed, those could all be good attributes of a design for space flight.
All right, thank you. And regarding material selection, are there any prohibited substances or any specific characteristics about the materials to make the recycling and transfer equipment?
This is Annie. I would say just keep in mind we want things to last as long as possible. So materials that are lightweight, durable, do not corrode, do not break down, but also do not off-gas and are not flammable. Those are your ideal candidates to be used in a spacecraft.
This is Mike. I might add, I think that was a good answer, and think about the low off-gassing and things like that. The only thing I can think of as far as prohibited materials is might be getting into some things like lubricants or things like that, or small particulates that could get out into the environment. So it's those kind of hazards that we want to avoid, but different types of metals and plastics in general are okay. Plastics, you have to think about the flammability aspects, but there's not a strict requirement on that, as long as some things that are flammable, for example, are often allowed as long as they're contained within something else. So they look at details like the potential ignition source and things like that. So those are good things to keep in mind in a design.
All right, thank you, Mike. Another question for your team. What is the limit of decibels allowed for the operation of this equipment?
Actually, before the NASA team gets to it, I'll take this one. The maximum allowable decibels is 80 decibels. Ideally, they would like to keep any noise generated by either the receptacle or the transfer mechanism limited to 50 decibels. Going up to 80 decibels is permitted as long as it's brief and intermittent. NASA team, does that pretty well cover it?
Yeah.
Yeah, it's definitely quieter the better, but understand that there might be brief periods when you're operating, say right after you put a new batch of trash in, where you would expect some additional noise there for the process. But definitely not at those high decibel levels around the clock.
All right, we have time for just a few more questions. We definitely are not going to get to every question that has come in today, so thank you very much, attendees, for an engaging session. Again, any questions we don't get to live, we will have the NASA team or the 9 Sigma team answer and include that in the transcript of the webinar. So, an important question for Jonathan here at 9 Sigma. Can we present a design idea for feedback or comments before the final submission?
Hi, I will say in general, I can't give individualized feedback on your proposal. That wouldn't be fair to anybody else who is submitting a proposal. What I can tell you is Number one, your submission has to be non-confidential in nature. Number two, your goal is to present interesting and compelling information that really describes the performance that your technology can achieve without indicating how that performance is reached. As I mentioned earlier, if your particular approach has some interesting capabilities on those additional desired performance criteria, go ahead and include that. If you've got videos of your technology in operation, that would be great too. Your goal in writing your response is to present to the NASA team information that demonstrates why your particular approach meets or, if possible, exceeds the performance criteria that they're looking for on the project page, to convince them that your particular approach is the one that they should consider.
Right, thank you. And a question for the NASA team, are there any specific consumables that should be avoided?
This is Paul. I would say in general, using consumables is not desirable. So I don't know that there's any specific consumables that are any worse than others, but you do want to minimize the use of consumables.
Okay, we will take 2 more questions, both for the NASA team. Is there any effect of microgravity on the recycling process?
Yes. The mechanisms that are being sought here need to be microgravity compatible.
I'll just add in, this is Jonathan from 9 Sigma. When you think about recycling here on Earth, the mechanisms by which a recycling facility can move trash from point A to point B for recycling can depend on gravity to assist it. There might be other mechanisms at work as well, but gravity may be able to play a role. So you might have a hopper loaded with trash, and the bottom of the hopper opens up and gravity pulls that trash down into a new component in the recycling facility. Whereas in a microgravity environment, you obviously can't rely on gravity to assist you. So you're going to need to consider mechanisms and approaches that are going to be able to move that trash from A to B without relying on gravity. That is the challenge here for you to address.
All right, thank you. And our last question back to the NASA team, is there a requirement for the total processing time for this 5 kilograms of waste?
This is Mike. So we came up with that number as an amount that they might load in a day, or in a short period of time, representing maybe a day's worth of trash. So it would need to be processed at least within 1 day.
Okay, thank you. So that concludes our live Q&A session. And again, any that we did not answer live will be included in the transcript that will be available soon after the webinar. So what can you do today? On your screens now is some final important information. You can see the web address for the NASA Recycling in Space Challenge page on 9 sites. Additionally, there is the email address and telephone number for the 9 Sigma Provider Help Desk. If you have a question about this contest or just need assistance with your proposal, the Provider Help Desk is ready to assist you. The email address is phd@9sigma.com. The phone number is +1 area code 216-283-3901. A key piece of information, the deadline to submit. Please be sure to submit your proposal online prior to the deadline, Wednesday, January 16th, 2019 at 5 p.m. Eastern Time. We won't be able to accept proposals after that time. This concludes our webinar today. One final reminder that this webinar was recorded and will be made available along with the Q&A transcript. Thank you to our speakers for their time and expertise. To our audience today, we appreciate your time and look forward to receiving your submissions and questions. Have a great day.